Streamed online, is it?
Yeah.
Have you shared it in Google Groups or something?
Yeah.
Google Groups has been shared.
Google Groups, are there?
Okay, we have a Google Groups beyond Riser also, no? All the alumni are there.
Yes.
Usually, if you do it online, we stream it online, we share it the alumni group also. When are you leaving for Riser?
I'm going there on 16th evening.
Actually, I'm also doing 16th. I'm in morning. My flight is at 10:45.
Okay. I'll be traveling by road from Amsterdam.
Oh, you go to TIFR?
Yeah.
In fact, Shoda from TIFR is in Japan.
Yeah. I heard
Sakshi is there. You didn't know your posters are written in a book. You didn't know your posters are written in a book.
Yeah.
So I will go through. No, she has sent me the details. I tweet it from Ceci as well as maybe from the A side account also. It's nice.
Yeah.
Video language, which is like very rare to have small book in officer. Pretty nice. Give me a coffee last Thursday or Friday.
Yeah.
Okay, so let's start. So we have with us today Saugata Barat. How to spell it? Barat or Barat?
Barat.
Yes. So he's pretty, I think, new in the game. Maybe I would say he did his bachelor's and master's for presidency university in Canada. And then he joined the University of Amsterdam for his PhD. A cool place. That's what we were discussing yesterday. So he's now taking a tour of India, giving talks about his work in various places. He's in Niger, then he's going to go to TIFR, then he's going to Pune. There is an exoplanet conference in Niger, Pune, sometime later this month. So he wrote to us, expressing his interest to give a talk here. So we're always happy to listen to exoplanets because it's something that we don't really have expertise as such. Traditional domain of exoplanets. Many of us work on the field, but not in traditional exoplanets. Welcome, Shobha. It's forward to getting over to you.
Thank you. Thank you for the introduction. I would start by thanking Nibelu, Sakshi, and Tobito for inviting me and helping to organize my visit here. I'm really excited to be here today and share my research with all of you. So, as Nibelu mentioned, my research focuses on studying the atmospheres of exoplanets. Specifically, my research focuses on studying the atmospheres of very young exoplanets. So the name you see here, V1298 Tau, it is a very young transiting exoplanet system, and you'll hear a lot about this in today's talk. The major goal of my research is to connect the observations of atmospheres of these young planets to our current theories of planet formation and early evolutionary mechanisms. This research wouldn't have been possible without my wonderful collaborators, all of whom are listed here. So planet formation is a very complicated and very interesting theory, and I do not hope to explain everything in detail, but I'll try to give a very brief overview of our understanding of giant planet formation. This theory is called core accretion theory. So the idea is, very early in the lifetime of a protoplanetary disk, small solid particles like dust and pebbles, they coagulate together to form larger solid bodies. As these solid bodies grow, they assemble pretty quickly within the first 1 million year or something. And as they grow more and more massive, they become large enough such that they can bind their surrounding gas gravitationally. So after 1 million year, this system starts growing by accreting solids and gas, and it keeps growing for about a few million years. After a certain point in time, something very interesting happens. So roughly, when the mass fraction of the solids and the gas in the accreting planet become roughly equal, it triggers an instability. This planet enters into a runaway gas accretion phase. It very quickly accretes all the gas in its surroundings, grows exponentially till the supply of the gas around it is exhausted. This is how we end up forming a gas giant planet. It is dominated by primordial hydrogen and helium.
So what kind of instability is that? Instability or
It is a gravitational instability. So it becomes so massive that it starts contracting under its own gravity, and the more mass it accretes, the more it contracts. So this is the instability that happens.
And so sound waves and pressure play a role also.
Yes, they play a very important role. Sound waves basically help to dissipate some of the energy of formation as it contracts. So there's a lot of heat, so it dissipates some of the heat through a shock current as it forms. So after the assembly of this giant planet, the disk has dissipated, and we formed a giant planet which is quite hot. So then this planet undergoes an evolutionary phase where it cools by radiating away its energy of formation, it contracts, and because these systems can be quite close to their young active host stars, because of the interaction with the star, it can lose a significant part of the accreted gas. And so with billions of years of evolution, these giant planets end up being the mature gas giants that we know of. So this is a very successful theory in explaining several observations in our solar system. But one thing we need to remember is solar system is just one system.
So I have this curiosity. So how do you end up as a Jupiter as opposed to Earth? I mean, what differentiates a gas giant from a rocky planet? Is the initial mass?
Basically, it's the time of assembly. Jupiter assembled when the proprietary gas was there, so it would accrete a lot of gas. But the terrestrial planet, on the other hand, is formed really late, much later than Jupiter, in fact. So the complete formation of the Earth was took roughly about 50 to 100 million years, whereas Jupiter assembled within the first few million years. So the gas was there. That's why it had time to accrete the gas. Whereas Earth, Venus, Mars, these are basically rocky cores that assemble very late and by collisions. That's why they do not have so much of primordial
Collisions between already solid matter? Or?
Mostly solid matter, yes. Yeah. So, as I was saying, this core accretion theory is mostly inspired by our solar system, but this is only one system. And in the last 2 decades, we have discovered more than 5,500 exoplanets. And it is one thing that we have learned from exoplanets is that planets are extremely diverse. Every system that we see has something that is unique to it. So, if we hope to understand the generalized picture of planet formation, we must take into account the properties of exoplanets. However, these exoplanets are really far away. So, at least in the near future, we do not hope to understand the physical properties of these systems in as much explicit detail as we know about the solar system. So, the idea is you want to look at exoplanets as a statistical population and infer trends about the planet formation population, about the planet formation theories in general by looking at the population of exoplanets. So this is a very favorite figure of mine from Fulton et al. In 2017. What this figure shows is it is showing the size distribution of planets that have been detected with Kepler. So one thing that you can see is that the so-called gas giants, which are planets roughly the size of Saturn and Jupiter, they are relatively quite rare compared to some of the smaller planets. So here we have detected a lot of planets between the size of Earth and Neptune. These planets are called super Earth and sub-Neptune, and it turns out that these are the most popular outcome of planet formation. So it's an important question because in our solar system we do not have any planet that is in between the size of Earth and Neptune. So why nature is so efficient at producing these planets and why we don't have any such planet in our solar system is a very important open question.
One question.
Yeah.
How do you take into account the biases?
So these are bias corrected, because normally if you just see a bias uncorrected picture of exoplanets, you see that we detect a lot of gas giants, but that's because they are so large and they are close in, right? So this distribution is bias corrected.
Based on what? How do you correct that?
So you can assign a probability of detection based on the size of the planet and its distance from its host star. Because all of the systems that you see here, they're very close in systems. They're quite different from our solar system. The periods of all the planets are less than 100. So these are compact systems, right? So if they're transiting, you can assign a probability that it will transit just from the geometry.
And all this data is from transit.
Yes, all the data that you see here, because you cannot measure the size of an exoplanet with anything other than transit. Is there any other question? Okay, thank you. Secondly, these comparing the gas giants and the smaller planets, there are some structural similarities between these smaller planets and the gas giants. Both of these planets have a solid interior core, and but the difference between these planets and the gas giants is that these gas giants underwent a runaway gas accretion phase, whereas they became completely dominated by hydrogen and helium and became much more massive. Whereas for these smaller planets, even though their solid core might be similar in mass to the gas giants, they did not undergo a runaway gas accretion. So there must be something fundamentally different about the formation mechanisms of these smaller planets which stops them from undergoing a runaway gas accretion. Lastly, I would request you to zoom into these smaller planets. Clearly, there are two distinct populations of these smaller planets. We have the smaller super Earths and the somewhat bigger sub-Neptunes, and they're separated by a valley of sorts, which we call the radius valley. So the idea is that from measurements of densities of these super Earths and sub-Neptunes, we find that the super Earths are mostly rocky. They do not have a significant hydrogen and helium envelope, whereas these sub-Neptunes seem to have some a small fraction of hydrogen and helium, which makes them puffier. So currently, we believe that the super Earths and sub-Neptunes had a similar formation, but after these systems formed, and their host stars were young, so they underwent a phase of very significant atmospheric mass loss. They would have lost a majority of the accreted primordial atmosphere because of stellar winds and stuff like that. So it is believed that this distinction is because of stronger evaporation, which led the super Earths to lose their entire primordial atmosphere, whereas the sub-Neptunes held on to a part of their primordial atmosphere. So it is very clear that early evolutionary processes play a key role in shaping the exoplanet demographics. These evolutionary processes can alter the imprint of the structural and chemical imprint of planet formation. So if you want to study the atmospheres of these small planets, it will be quite tricky to connect those observations back to planet formation, because the evolutionary process in between is quite uncertain. So here's where, yeah.
And a quick question. What's really the origin of the radius value between the super Earth and sub-Neptune? Like, I understand the difference in the gas accretion leading to a difference in the atmosphere. But how do you explain pure number?
So basically, when super Earth and sub-Neptunes were formed, they would have a similar amount of hydrogen and helium. The formation is not very different. But what we see is that, so I may have a slide back somewhere. Yeah, so if you see that this is a zoom in to the planet size versus orbital period. So these are the super Earths here. So you see that the super Earths are statistically much more closer in to their host stars, whereas here the sub-Neptunes are not there. So this is an effect of stellar flux evaporating out the atmosphere, right? So
that's the popular widely accepted.
This is the most popular widely accepted theory. Yeah. So basically, anything that was here would have lost its atmosphere very vigorously and become mostly rock. So there would have been an evolution from here down to here. That's why you basically see that gap in between. Yeah. Right.
Are there examples of observations of exoplanets, planets which do not come from that popular explanation?
Yes, that's a very good question. Indeed, there are. There are some, very few, but we have some planets which are there in that gap, which we call the Neptune desert. And those are like planets which are very weird, and they are undergoing observations with JWST currently. So yeah, we have to see. Maybe they are a different class of planets, but yeah, we do not have an answer to those planets. So as I was saying, that this is where the young planets become very important. So by young, I mean planets which are younger than 100 million years. So just for context, our solar system and all the other planets that I showed, they are few billion years old. So these planets are really very recent products of planet formation. And at such young ages, we only have a handful of transiting young planets, all of which I have shown in this diagram. So this is a diagram showing the radius versus period, and the contours in the background, they are for the mature planets. So all the young planets, young transiting planets that we have, they fall in a somewhat rarefied part of this parameter space. All of them are lying above the radius value, which means that they are likely to harbor some sort of a primordial atmosphere, which makes them puffier. As they are young, they're likely to lose mass, lose heat, and contract. And according to our current understanding, we expect them to evolve and end up somewhere here, being a sub-Neptune or a super Earth. So, of course, these are the planets that are ideal to understand the outcomes of planet formation and characterize in detail the early evolutionary process, because they are undergoing the process currently, right? Before talking about more young planets, I will digress a little bit and give a brief overview of a technique called transmission spectroscopy, which I will be talking about a lot in my talk. Some of you may already be aware of this, so please bear with me. So here what you see is a picture of Earth taken from a satellite, and the halo that you can see here, that is the atmosphere of the Earth. So this is a picture that has been taken with optical, right? And our atmosphere absorbs optical photons and also scatters optical photons. That's why you see the atmosphere like this thin slice. But the size of the atmosphere depends on the absorption cross-section of the constituents of our atmosphere, right? So if you were to take this image in some other band, say infrared, the size of the atmosphere would inherently be different, right? So this is the idea that we carry forward to exoplanets. So in case of exoplanets, if luckily the orbital plane of the planet is aligned along our line of sight, these planets as they pass in front of their host stars, they will block a part of the starlight, and that will be manifested as periodic dips in the stellar light. This is how we detect planets in the transit method. Now, if we move a step ahead and take these transit measurements at different wavelengths, this basically gives us an idea of the radius of the planet at different wavelengths. Of this planet, which are absorbing, it gives us an idea about the size and temperature of the atmosphere as well. So this is briefly what we do in transition spectroscopy. So coming back to young planets, so I'll introduce you to my favorite young planetary system. It's called V1298 Tau. It is just 23 million years old. It is a weak-lined P-Tauri star. It's a three-main sequence star, and it harbors 4 transiting planets. So the 4th planet in the system, we really don't know much about it because its period is still unconfirmed, at least till now. So this is actually the youngest system to host more than 2 transiting planets. So first, I will dive deep into the 3rd planet in the system, which is called V1298 Tau b. It is a Jovian-sized planet. It is roughly 670 Kelvin with its equilibrium temperature, and it orbits its host star in 24 days. So what did we do? We observed one transit of this planet using the Wide Field Camera 3 on Hubble Space Telescope. I will not go into a lot of detail about the observation, but try to give you a broad understanding of how this really works. So here what you see is a raw image of the detector from HST. In this direction, we disperse the starlight. So essentially, the spectrum is in this direction, but because the star is quite bright, the detector can saturate. So Hubble has this mode where it can scan the source, right? So it avoids saturation. That's why the spectral trace looks like a rectangle. So we take 180 such exposures over a period of 12 hours for this planet, and what we end up with is a light curve that looks like this. So this is actually a broadband integrated white light curve. You can clearly see the transit of the planet here, and the egress and ingress is also covered by. The chunks of data that you see here, these are for individual orbits of HST separated by gaps in between. That is, HST is in a low Earth orbit, so it gets occulted by the Earth from time to time. And the hook-like structures that you see in each orbit, that is an instrumental systematics that is quite well known for HST. These are charge trapping effects, and over the years we have developed the expertise to model these and deal with this. So for this set of observations, the main challenge is actually the star itself. Because if you look carefully, if you look at the orbits which are out of transit, it's not really flat. You see that the stellar mass itself varies with time. And this is because this is a very young star. It has a very large spot coverage and it rotates very fast. So it has significant rotational variability. That's what you are seeing in the stellar baseline. Also, because the star is so active, we saw an effect of a spot crossing. So the planet effectively went in front of a star spot in this orbit. In this orbit, there might have been possibly a tiny flare also. So what I'm trying to say is that there are a lot of stellar effects that are happening on this star, and that complicates our job. And we spent a significant amount of time trying to assess what are the effects of these stellar variability on our transmission spectrum. And I will not go into the details, but trust me that we did a comprehensive job in doing that. So, yeah.
First one, the first one is the raw data.
This one, yeah.
No, the second.
This one?
Yeah.
Yeah.
And then you are getting the disk profile by doing the correction. The transit.
The transit, no, I mean the
So
transit.
what's the second?
Here we do not do any stellar correction, right? So what we are doing here is that you have the spectrum here, right? So we are basically summing up the flux here. This is wavelength integrated. So you're basically taking the sum of all the electrons that you have detected, and that's your time series. So that's all that is here. So on this time series, you are seeing the effects of the star, and the corrections that I'm talking about that happen actually later when we derive the transmission spectrum. We basically go back and forth and try to see that what effect these spot crossings or a microflare has on the derived transmission spectrum. Here we have applied no correction.
So what's the second plot?
Okay, so I didn't go into this. This is basically showing you the technique that we use to detrain the spectroscopic light curves that you see here. All the systematics are gone, right? So we basically detrain the systematics from the spectroscopically bent light curves using information from the broadband white light curve. What we do is we have a model, a very crude model, and we fit this transit light curve with that, and we derive something called the systematics function, which is shown in this figure, right? So we do not care about the exact mathematical form of this, but we make an assumption that these instrumental systematics are wavelength independent, and turns out that it is a decent assumption. So using that, we remove the systematics from the spectroscopic light. So that is what we are doing. Yeah. Yeah. One slide back. Yeah, sure.
Star itself, V1298.
Yeah.
What is it?
The mass of this is 0.9 solar masses.
So the scaling laws, mass is small, age is quite large. So how do they observe the age of this particular star frequency?
Yeah, it's a good question. So this star is part of a moving group. So most of the young stars that we find, they are part of some sort of a moving group. So you basically do an isochrone fitting to the stars, and that basically gives you an age of the moving group. That's how you do it. And there are other indicators of age. For example, lithium line is a good indicator of age of a system. This shows very significant rotational variability. It has a rotation period of 2.8 days, which is quite fast. So all of these combined together tell us that it is a young star, but the precision on the age comes from isochronal fitting. Is there any other question? Okay. Okay. So I will ask you to take a leap of faith and believe in me that we were able to detrain these effects from the spectroscopically bent light curves, and we arrived at a precision of within 20% of photon noise. We fit all these individual spectroscopic light curves, which gave us our transmission spectrum. So this is the star of the show today. This is the transmission spectrum of V1298 Tau. On the y-axis, what you have is the radius of the planet divided by the radius of the star whole square. That is what we derive from our transit light curves as a function of wavelength. So what you see here around 1.4 micron is a very large absorption. You see the size of the planet is larger in this wavelength. And this absorption feature is due to water vapor. So we are actually reporting a detection of water absorption in the atmosphere of this planet at 7 sigma confidence. The size of this absorption feature is almost 400 ppm, which is one of the largest water absorption features that has been detected with Hubble Space Telescope till date. What this tells us is that this planet is a very large extended atmosphere with a scale height of roughly 1,000 kilometers. So for context, the scale height for Earth is only 20 kilometers. So you can imagine how large this atmosphere really is. So given the high precision on the transmission spectrum, what we do is we try to characterize the properties of this planet. First, what we do is we try to measure the mass of this planet. the idea behind this is really simple. If the planet has a larger gravity, it will make the atmosphere compact. On the other hand, if the gravity is weaker, the atmosphere can be more extended, right? So, from the transmission spectrum, we have a good handle on the size of the atmosphere. And we can relate the size of the atmosphere to the mass of the planet using this relation, which is very simply derived by assuming a hydrostatic equilibrium. So, from this method, we estimate the mass of the planet to be 24 Earth masses. You see that I've quoted this as an upper limit. This is because we have a simplifying assumption of that this atmosphere is here. There are no clouds in this atmosphere, but that may or may not be true. So, in case there are clouds in this atmosphere, this approach will provide us with an upper limit for the mass. So, the mass can be smaller than 24 Earth. So, but this is a very unconventional way of measuring the mass of a planet. People usually go the other way around. They measure the mass, and then from that, they fix it when they are trying to infer properties from a transmission spectrum. So, we did observe radial velocities for this system. Yeah.
So the mass is derived also assuming a isothermal atmosphere,
Yeah,
or how big of assumption is that?
That's not a very bad assumption, because we are sensitive to a narrow pressure range in the atmosphere. So you basically are looking at from 1 millibar to say 100 millibar. So that's not a very massive pressure range. So the atmosphere is essentially dominated by these stellar radiation. So you can safely assume it to be isothermal.
And the mu there is considering the average composition.
Yeah, mu is the mean molecular weight. So because this is a young planet, we assume that it is mostly composed of hydrogen and helium. So for most for most metallicity values, the mean molecular weight is roughly 2.33. So that also does not vary a lot unless your metallicity is very high. So that is also an assumption that can be justified. So, as I was saying, that we observed radial velocities for this planet, and turned out that the mass estimate from radial velocities was extremely high. We found 200 Earth masses with an uncertainty of 50. So, just to guide the eye, if you look at this black dashed model, this is a transmission spectrum model using a 2 sigma lower limit from the radial velocities. And even for a 2 sigma lower limit, the gravity is strong enough that it makes the atmosphere significantly compact, and we can rule out a 100 Earth mass atmosphere with very high statistical confidence. So there's another independent way of measuring the mass of this planet, that is with transit timing variations. So transit timing variations occurs in multi-planet systems where the different planets gravitationally interact with each other, and the period of the planet changes very slightly. So it can sometimes transit before the predicted time, sometimes later. So that is basically a transit timing variation because of gravitational interaction between multiple planets in the system. And because this is a multi-planet system, we have this effect. So independently, those results are agreeing with the upper limit that we are setting from the transmission spectrum. So the question that arises is, what is going wrong with the radial velocities? So again, the answer is that this is a very active star, and the issue is the spectral lines which are used to calculate the radial velocities. Those are very highly variable. As a result, it can induce a spurious signal in the radial velocities, which can inherently bias the mass measurement. So radial velocities is the workhorse of our field for mass characterization. But it turns out that this will be a problem for most, in fact, all of these young planets. And we will not have transit timing variations as a savior for all systems, because most of the young planets are single systems. So this technique of using a transmission spectrum to put constraints on the mass of a young planet is going to be very important and game-changing for this class of planets in the coming years.
So,
yeah.
one small question.
Yeah.
So, what's the implication of being cloud, being or not being cloud they're thinking about?
Yeah, that's a so.
Droplet cloud or something else?
It can be, actually it's not likely to be water cloud because it's way too hot for water clouds. But you can, like, at this 600, 700 Kelvin, you can have magnesium silicate clouds and stuff like that. So what clouds do is clouds have a very high opacity, right? So they block any light that is falling. So if there's a cloud deck at a particular level, what it will do is, if the transition spectrum is supposed to go like this, it will flatten it out. So the effect of the cloud will be that we will be underestimating the size of the atmosphere. That's why the mass that we have here is an upper limit. Yeah.
Yeah, this motion of a planet around the star as well as its own rotation.
Yeah.
Does these two affects these spectrum?
It's a very good question. The orbital motion does not have any significant effect on the spectrum. Like the temperature, which is determined by the semi-major axis, that of course has an implication on the atmospheric chemistry. But the spin that you said, that is a very interesting point, because till now we've been studying mature planets which are most likely to be tidally locked. So for those systems, the rotation is not that important. But because the system is 20 million years old, it's unlikely that this will be tidally locked. So it might have a high rotational velocity, but that will not have such a high impact on this low resolution transmission spectrum. What it will have an impact is, if we take a very high resolution spectrum of this planet's emission, it will have a broadening effect on the planetary lines. And that, although there is a hard effect to measure, we are attempting to do that with high resolution spectroscopy. So yeah, indeed.
So you can see individual lines.
We can see individual lines with very high resolution spectroscopy. Here, what we are seeing is a broad band. This is low resolution space-based spectroscopy, right? So here we are basically seeing rotational vibrational bands of water capacity.
What is this?
For high resolution? So for high resolution, there are several high resolution spectrographs. So there's one instrument called Carmenes, which is on the color alto. In Canada, there is an instrument called Spew. So and there's another one called Espresso. So there are,
right? Or is it European collaboration?
Carmenes is European collaboration. Yeah. So typically you have like resolutions of 100,000 in those spectrographs. Is there any other question?
And JWS is going to have some contribution to this, or
JWS is also
space-based stuff. Right?
Yeah, it's also technically low resolution. So the highest resolution that you can have with JWST is roughly 3000.
What are the apertures for the mirrors in the Spiro and?
Well, I do not remember that from the top of my head, but I would guess that there would be like 4 meters, I think. Yeah. Yeah, and like with JWST, there are some attempts to try to do some high resolution, but yeah, it's only 3000, so there are limitations to that. If there are no other questions, I can move on to my next slide. Okay. So, so in this diagram, I'm showing V1298 Tau B on the mass radius diagram with in the context of the mature exoplanet population. So as you can see that if you compare the position of this planet on this diagram, it really has a very low density. It is in fact one of the lowest density planets that we have discovered till date. And the mass measurement that we have puts this planet as a possible Neptune or sub-Neptune progenitor. From the mass measurement, we can definitely say that it is not a gas giant. This is a young Neptune or potentially sub-Neptune kind of a planet. Comparing the mass and radius of this planet with structural models, we find that we require a very high amount of hydrogen and helium to explain the mass and radius of this system. This is a very key point, and I will come back to this later in my talk. Okay, so changing gears, I will talk about another measurement from the spectrum. So as I said that this absorption is due to water. So next what we try to do is try to measure an abundance of water from the spectrum. So just a heads up that in my later slides, I'm going to talk about water abundance and metallicity sort of interchangeably, because oxygen being the most abundant element after hydrogen and helium, the oxygen abundance in the form of water is a good indicator of the total atmospheric metallicity. So the blue line that you see here is a 1D radiative transfer model that we have fitted to the observed spectrum, and we find that our models converge to solar metallicity. So just for context, here is in orange we have a model with 100 times solar metallicity. What happens is at such high metallicity, which is actually quite typical for Neptune mass planets, the mean molecular weight is very large. So that also has an effect of compacting the atmosphere. So high metallicity atmospheres can also be confidently ruled out. Of course, you may ask that the mass and metallicity, both of them have an impact on the spectrum, and that is true. There is a degeneracy between mass and metallicity. So the metallicity is also, in fact, a limit, I should say, because we ran these Bayesian retrievals for different masses from 24 Earth masses all the way up to 10 Earth masses, and we found that for all of our simulations, we converge to solar and possibly even sub-solar atmospheric metallicity. So this is a diagram where I'm showing V1298 Tau in a mass metallicity diagram with other known exoplanets with atmospheric measurements, and also the solar system planets here. So based on our understanding of core accretion theory, we expect a mass metallicity trend to look like this. This is because smaller the planet is, the lower is the hydrogen and helium that it accreted, so it is more metal rich. So smaller planets, higher metallicity. So if we compare V1298 Tau with Uranus and Neptune on this diagram, it is deficient by almost 2 to 3 orders of magnitude in terms of its atmospheric metals. That's a huge deficit. So putting all the information that I provided to you till now on one slide, V1298 Tau is a Neptune or a sub-Neptune progenitor, or it could even end up as a super Earth depending on how aggressive its atmospheric mass loss is. So what that implies is that this planet would have formed pretty close to its current location with respect to its host star. And I'm saying this because if it had formed very far away from its host star, the gas accretion efficiency would have been higher, and it would have been harder to stop a runaway gas accretion for this planet. Mind you, the hydrogen and helium mass fraction is between 30 to 40, so it is very close to runaway gas accretion. So it's a very unique system with that respect. So it's very likely to have formed in the inner part of the disk. It could have had a late assembly, which basically means that this point here, where the solids have already accreted, that point for some reason would have been delayed, and if this point didn't occur in 1 million years, it occurred sometime later, then the planet would not have enough time to accrete so much hydrogen and helium to reach runaway gas accretion. So that's one scenario that is possible. On the other end, it could have assembled early on in the lifetime of the disk, but this gas accretion, that would have been slower compared to what we expect. There are several theoretical ideas to slow down the gas accretion rate, which I'm not going to go into because that's a talk in itself. But if you're interested, I can discuss about that later. Second important point: this planet is extremely water cool. So either this planet would have had a very unique quirky formation scenario which would have led to it being born as a very dry planet, or what we are observing is an evolutionary effect. So let me go into a bit more detail about that. So in the first scenario, where the planet is, where I'm saying that the planet would have been born dry, so let's think about the formation of a subneptune. So the water content of a Neptune-like planet that depends on where the assembly of the planet took place in the disk. So in the disk, there are some very critical regions. So there's something called a water ice line. That's the point in the disk where water freezes out. So imagine that this subneptune formed beyond the water ice line. So in this case, it has access to solid particles which have volatile ice condensed on them. So basically, you have solid particles which are rock and ice. So you have ample supply of water. The solids will bring in a lot of water, and you will end up producing a very water-rich planet. On the other hand, if this planet formed inside the water ice line, it could still have accreted water, because these small pebbles, which are water rich, they migrate through the disk. And as these pebbles would have crossed the water ice line, they would have sublimated their water into the gas phase in the inner part of the disk. And as the subneptune accretes that water-rich gas, again, it has water in its atmosphere in ample quantity. So a third scenario where we take into account that this is a multi-planet system. So if there is a giant planet that is forming beyond the orbit of this Neptune, what it can do is it can create a gap in the protoplanetary disk and stop the influx of these pebbles towards the inner part of the disk. So essentially what it will do is it will deprive the inner disk of volatiles and make the inner disk pretty dry. So all the planets that are formed in the inner part of the disk will be dry. So this is a prediction from this model that not only V1298 Tau b, we would expect all the three inner planets to be quite dry. So this also, of course, depends on what the mass of the planet E is, and at this point we have no idea what it is. Yeah.
When you were showing the spectrum,
Yeah.
you mentioned that it has the strongest water line.
Yeah. Strong. It's not the strongest water line. I should clarify. The size that you see in transmission spectroscopy, that is determined by the size of the atmosphere, right? So it is so large because the height of the atmosphere is very big. But the abundance of water that comes from fitting the shape of this spectrum as well, right? So we basically got the water abundance by comparing it to for like theoretical forward models. And
The abundance is basically a free parameter that will vary in the models until you
basically fit the spectrum. Yeah.
It's basically reduction.
Yeah, this is basically like you run LCMC and fit the spectrum.
Can you explain the y-axis bit? Because I thought that is some representation of the intensity.
No. Okay. So the y-axis is basically the radius of the planet with respect to the radius of the star, right? So how you're getting that is, Yeah. So you have this spectroscopy light, right? So you're fitting them, and the depth of the transit that gives you the RP over R star square, because the amount of light that the planet drops is basically the area of the planet's disk, right? So you basically have the area of the planet's disk divided by the area of the star's disk.
And as the radiation changes, the disk size changes.
Exactly, the disk size changes. So that basically gives you the information about the atmospheric opacity. Yeah.
I think I don't know how many done the astrophysically scores, but this is in the station to ongoing research. Right. So possibly encounter say atmospheric models and the astrophysics scores. Yeah, so you probably hear about this kind of stuff. Spectral and formation and things like this.
Okay. So as I was saying that in this theory that we call Pebble filtering, you essentially have a prediction. Yeah. So essentially in this Pebble filtering model, because of the influence of the outer planet, we can produce very dry planets in the inner part of the disk. So this is something that we can test. On the other hand, we could have formed a planet which did accrete enough solids, but we are just not being able to see them. So let me elaborate that idea a little bit more. So the chemical structure of the atmosphere is actually dependent on how the accretion happened. So, for example, if the accretion proceeded through accretion of very large solids like boulders, then our simulations show that the structure of the planet is sort of a very sharp. There's a very sharp distinction. You form a core and an envelope. This is the structure that you get if your accretion proceeds by very big structures. On the other hand, if the accretion happens through smaller particles like pebbles, as these smaller particles fall through the atmosphere during the accretion phase, they erode away. So that naturally produces a metallicity gradient in the atmosphere. The upper atmosphere has lower metals, where most of the metals are sequestered in the deeper part of the atmosphere. Now, something to remember is that these planets are not going to look like this forever. They are going to lose a lot of their upper atmospheres because of stellar radiance. So it is possible that this upper metal core layer will be removed. And as this planet evolves and matures over the next few 100 million years, we will end up in a situation like this, which will reconcile V1298 Tau b with the mature sub-Neptune population. So, what is the prediction about the other planets from this model? This model predicts that the inner planets will have a higher metallicity compared to V1298 Tau b, because the closer they are to their host star, the more vigorous is the mass loss. So this gives us a direct testing mechanism to compare the atmosphere of the different planets in the system and basically break the degeneracy between these two possible scenarios. That sounds quite simple. So we did that. We observed another transit of the innermost planet V1298 Tau c, which is roughly half the size of planet B with an equilibrium temperature of 1000, and it orbits its host star in around 8 days. So actually, the observations of this planet did not go according to plan through no fault of ours. We are actually very unlucky with this observation. So why, I will tell you. So I will draw your attention to this figure where we are showing the test light curve of V1298 Tau. You can very clearly see how variable this star really is. It shows significant rotational variability. It's a mess. Let's put it that way. And so the transit that we are observing, that actually happened here. So zoom in, you'll see that the stellar baseline is changing very significantly. In fact, we find that the stellar baseline, the slope of the stellar baseline is more severe compared to what we had in the planet B scenario. So that's one challenge. Secondly, you might be very surprised to see this first orbit. It's much larger in systematics compared to the other ones. And we didn't have something like this in the planet B light curve. That is because in planet B, the first orbit had been discarded. This is actually something that is a very known problem with HST, that the first orbit has much larger systematics, which shows very strong gradient dependence. So it's typical practice to remove that from our data analysis. But here what happened was, when we observed this system, the TDE models were not mature enough. They were not perfect. So the predicted mid-transit time was not accurate. The transit occurred 2.5 hours before what we had predicted. So we did not get any pre-transit baseline. So the transit is here, and if we had at least one decent orbit before this, we would have been good to go. But we got just this orbit. And that put us in a very difficult situation because all the techniques that we had developed for planet B do not work here. Because this orbit has such strong wavelength dependence that we cannot remove the systematics by assuming a common mode correction. So we tried to model this line curve that was a challenge, and we did end up doing it, but we paid a price, a very heavy price. That is, because of the large curvature and because of the inaccurate modeling of the first orbit, the error bar, the uncertainties on the transit depth that we got were much larger than what we had expected. The error bars are actually 1.5 times larger than what we had for the planet B case. So that really messed up our observations. I mean, if you look at this transmission spectrum, you may start to see that there may be some sort of an absorption here, but because the error bars are so large, it's really difficult to conclude anything. So we compared different models to this observed spectrum, and we compared an absolute flat line to see statistically what we get. And it turns out that we have a very tentative 2.5 sigma detection of water for this, but that's not significant to make any claims or differentiate between the models that we proposed. So I'm a very optimistic person, and I see this as an opportunity to convince the TAC that there is something there. That's what this observation tells me. So we need to re-observe this. That's the bottom line from this. So I don't want to end on a sad note of bad observation. I'll come back to the spectrum of V1298 Tau B. So I talked about the mass, I talked about the metallicity, but I skipped over something. If you look at the end of the spectrum, it is relatively flat. But in this part of the wavelength, you expect a strong methane absorption signal. And because I agree that these 2 points are pretty much at the end of the detector. So sometimes there can be questions regarding whether it's reliable or not. But because the height of the atmosphere is so large, the models which have methane can be ruled out with pretty high statistical confidence. So this is very surprising, and I'll explain why. As I said, the equilibrium temperature of this planet is 670 K, and carbon chemistry is actually very sensitive to temperature. So if you look at this pressure temperature diagram, it is divided into 2 parts. At higher temperatures, most of the carbon goes into carbon monoxide if you assume equilibrium chemistry. On the other hand, at lower temperatures, all the carbon is locked up into methane. And the solid lines that you see here are self-consistent temperature pressure profiles for V1298 Tau B. And this planet is deep into the methane-dominated region. So in transmission spectroscopy, you are basically looking at this part of the temperature pressure profile. So it's very non-intuitive why we do not see the methane. There are some potential explanations to this, which invoke some disequilibrium chemical phenomenon. So one possibility is that the atmosphere gets hotter deeper into the planet because there's a planet's flux as well, right? So as you go to higher pressures in the atmosphere, you have much higher temperatures compared to the upper atmosphere. So it's possible that at some point you can cross over to the methane poor region. And if these atmospheres have significant vertical mixing because of convection and stuff like that, it can happen that it can pull up methane poor gas from the deeper part of the atmosphere up to the observable pressures. So that has been proposed to actually explain the non-detection of methane for other planets. Yeah, I'll wrap up very quickly. I have 2 or 3 slides. Yeah, so I'll go very quickly. So that is one possibility, but we need very high temperatures to explain that. On the other hand, another possibility could be that you could have, because it's a young star, there could be a lot of ultraviolet light which triggers photochemistry and dissociates methane. So these different scenarios can be tested by JWST observations. So we have one transit with near-spec G395 for this planet, and this is basically the kind of spectrum that we expect. This is from WASP-39b, which was published by the early release science community. So we'll be sensitive to water, we'll be sensitive to carbon dioxide, carbon monoxide, and also sulfur. So we'll have a very good constraint on the atmospheric metallicity, the carbon content, and also photochemical processes. So this is going to be very exciting in the coming few months. So I would like to conclude my talk with my take-home message. So we know that V1298 Tau is definitely a Neptune, sub-Neptune, or likely to be a super Earth as well. The atmospheric metallicity is very puzzling, and there are different scenarios to explain this. But to test which one is correct, we need to observe the other planets in the system and also other young planets as well. Because for me, this study is really a pilot study showing that indeed we can get information about young planetary atmospheres in the backdrop of extreme stellar activity. That was a huge challenge in the beginning. But we can do it because the atmospheres are so large. So we will have observations of other young planets definitely in the coming years. And I think that will help us in understanding the atmospheric evolution in terms of structure and composition. We need direct measurements of mass loss rates because atmospheric mass loss is an unconstrained phenomenon, to be fair, and direct measurements of mass loss rates can help us predict the evolutionary tracks of these planets. And last but not the least, I think a lot of people here will appreciate that these stars are young stars. They are pre-main sequence stars, so their spectra are expected to be quite different from what we have. So now, when we model the mass loss or even photochemical processes, we are using ACDs from mature stars. But there's a need to directly observe the XUV spectrum of these stars to put as inputs for our theoretical models. And Hubble can do it, but it's a telescope that is aging and it's very oversubscribed. So this is an opportunity to use other telescopes in the XUV regime to get these stellar cities. And I think AstroSat is one such telescope which might be very useful. So with this, I conclude my talk, and I'm happy to take questions.
Thank you, sure. But before we ask questions, we see a lot of new faces here. I'm just kind of curious. How many of your undergrads, like your students in the same class, are okay or? So you guys are doing astrophysics course. Yeah. Sorry. Okay. Okay. All right. How many doing astrophysics studying? Yeah, this year Raj is back to class. IPU students, then IPUs. Alright, so while
There's an announcement, he is waiting outside, so
we are probably all hungry now. But anyway, please do have people to go. Questions. I mean, we welcome students to ask questions and have a discussion. So it's going to be available here all day after lunch. So maybe after 2:30 we'll be back in Sasi. He's going to be in the other room, the students and posters.
Please feel free to just come talk to me.
PhD prospects and things like that.
So can I ask you? What is this? Is it a new understanding that it is possible to have a Jupiter-like system planet, and then it can go on to collapse to become more solid? Or?